Hi, I'm Zor. Welcome to Unizor Education. We continue talking about functionals and their extremums and how to find these extremums. Now, the previous lecture was about one particular functional, which is the length of the curve from one point to another. Today we will expand the basically repertoire of functionals for which we can find extremums. And we will finally derive certain differential equation called Euler-Lagrange Equation, solution to which are the functions which derive this functional's extremum. But we are talking about particular functionals. I will explain what kind of a class of functionals we are talking about, and obviously particular type of functions where these functionals are defined. Okay, so first let's talk about functions. Functions f of x is presumed sufficiently differentiable, defined on segment AB, where a and b two real numbers, any real numbers. And what's important is they are fixed at the end. So all the functions which I consider, let's say this is class omega. It contains all the functions defined by all the functions f of x where x belongs to this particular segment, and also they are all having on the left end value a capital and the right end of the segment value capital B. Again, this is kind of a trajectory from a point to a point. For example, you would like to minimize amount of fuel which you're spending from one point to another in space, and let's say you have a gravitational field, in which case it's not a straight line actually. The optimal would not be a straight line, it would be something else. And you would like to find this something else, the trajectory which gives you an optimal fuel consumption. So that would be kind of functions we are talking about. Fixed ends and differentiable sufficiently. So functions we have defined. Now what kind of functional we are talking about? Well, the functional which very much typical for physics, for problems related to physics, and that's exactly why we are talking about functionals. It's all physical applications. We are talking about functionals of specific type. Okay, this is the type of functionals which we are talking about. So as our object is moving along the trajectory defined by function f of x, there is certain formula which gives, let's say, amount of fuel consumed, and the formula depends on trajectory and on first derivative of this trajectory. So you have this kind of a formula which is derived from some physical concepts, which integrating with integration from a to b gives a functional, which a function of a function, where f of x is the function we are looking for, and we are looking for a particular function f0 which minimize or maximize the functional phi. Okay? How do we do it? We do it exactly the same as I was talking in the previous lecture about if my functional is just the length of the curve. So what I did was I stepped from f0 to some kind of a neighborhood function f1, and then I will move from f1 towards f0, and since f0, let's say, it's a minimum, supposed to be a minimum, let's say, of the functional. Now, the way how I move can be dependent on the parameter. So I will have a function g of xt is equal to f0 of x plus t times f1 of x minus f0 of x. Now, as t is equal to 1, my f0 plus f1 minus f0 would be f0, would be here. This is at t is equal to 1. And if t is equal to 0, I will have, this is 0, so I will have only f0. This is at t is equal to 0. So as t is equal to from 1 to 0, my function would be, well, let's say we're talking about a minimum. So my function phi of g of x of t would be, okay, as t goes down to 0, this would be to a minimum, right? If t is going down to 0, from 1 to 0, my function of g would be closer and closer to just function f0, where it's supposed to be a minimum. So that's why this is reaching a minimum as a function of t if t is equal to 0. Now, what does it mean? Now we have a function of t, not functional of function g or f, etc. What if we just completely don't pay attention to x at all? We just move down with t from 1 to 0. And that's a regular function of one argument, real function of one argument. So if I will have a derivative of this by t, it's supposed to be equal to, at point t is equal to 0, it's supposed to be equal to 0. So this is something which I'm going to calculate, and then since my g, which is dependent of f1, now it's supposed to be for any f1, so no matter from which direction I'm moving towards f0, I still have to have this thing. So the f1 should be arbitrarily chosen, and we still have to have this equation to be true. And that what gives us basically a differential equation for f0. Okay? So next is we just calculate the whole thing. Next is just a technicality. I will differentiate whatever the function is using this, and then we will derive to equation. The only thing what I will do, I will replace this with delta of x. So delta of x is f1 of x minus f0 of x. And what's important, delta of a is equal to f1 of a minus f0 of a, but both of them are a. So this is 0, and so is delta of b. So delta is an increment, basically, which has 0 on both ends. All right, fine. So we've got that. So let's do this differentiation of phi of this first as a function of t. Then we assign t is equal to 0, and whatever will be the result, it must be equal to 0 for any delta which satisfies these conditions. Okay, so again, as I was saying, everything else is technicality. Now, differentiation by t of phi. Phi is an integral by x. X and t are completely independent variables, right? So I can interchange. For example, if you have differentiation by sum of two functions, you don't have any hesitation to put it as a sum of derivatives, right? So derivative of sum is equal to sum of derivatives. Integral is a sum. So basically you understand that it's supposed to be interchangeable. Integration by x and differentiation by t must be interchangeable. So I will put inside. So now I will have integral from a to b and differentiation by t of f of x, g of xt, and g prime of xt. And this is by dx. So that's my That's my order. Okay. So that's my integral. Okay. Now, how to do differentiation by t if you have a function of three different arguments? Well, it's a partial derivative by first times derivative of the first argument by t plus partial derivative by second argument times derivative of the second argument by t, and the same thing with the third argument. Okay, so it's equal to, well, differentiation, partial differentiation by first argument, it's df by dx times differentiation from x by t. Now x and t are independent variable, x does not depend on t, so it's 0. So the first first term of my sum of three terms is equal to 0. Now the second term is equal to integral from the b, differentiation of partial differentiation by second argument, so it's df by second argument df, and then instead of f I should put g of xt times derivative of g of xt by dt. Now g of xt is equal to f0 plus t times delta of x, right? So differentiation by t gives me delta x. By dx. Now plus the third parameter. So it will be df by df prime, the third parameter, where instead of f I should substitute g of xt times derivative of this by dt. Now again, if g of xt is equal to f0 plus t delta, now first derivative, derivative by x, right? So that would be the same. And now derivation by t will give me this. So it's times delta prime of x dx. Okay, so that's my derivative by t. Now, if I will substitute t is equal to 0, I should have 0. Because t equal to 0 is point of minimum, right? So derivative by t at t is equal to 0, where my g of x and 0 is equal to, my g of x 0 is equal to f0, the minimum point. So that's where it's supposed to be equal to 0, this derivative. Now, a little step backwards. If only one integral instead of two I will have, as I was saying, delta x must be any increment as long as it's equal to 0 on both ends, right? Because I can step from f0 to f1 in any direction, so my delta x would be increment in any direction. Now, if something times any function gives integral to equal to 0, obviously the only way to achieve it would be this to be equal to 0. Otherwise, if it's not equal to 0, then I can always find some kind of a function delta x so that integral is not equal to 0, right? So if at any point this function is not equal to 0, let's say it's this type of a function, well, then I will have a delta x which is equal to 0 everywhere else and 1 here, and smooth it somehow at the end. So integral will definitely be greater than 0. So again, this one integral would be simple. Now, but the second integral is slightly kind of spoils the picture, right? But I can actually change it in such a way that the second integral would also be dependent on delta x, not delta prime, not the derivative. How can I do it? Very simply. Integration by parts. U dv is equal to uv ab minus integral v du. Well, I hope you remember this formula from calculus. I will use it, where this would be my u. Now, delta prime of x times dx would be my dv. So I will exchange. So how should I use this formula? Okay, first of all, I should put their multiplication uv. So uv would be whatever this function u times v would be now if this is g delta of x, right? So v is equal to delta of x. Now u is this piece, and this is my v. So it's uv from a to b minus integral from a to b v du. v is delta of x, and du is differential of this du. So differential of function is its derivative, so I will put d by dx of partial by third argument times dx. So this together is d of this function, d of this function. Now, delta of x is equal to 0 at a and 0 at b. Otherwise, you know, this delta is f1 minus f0. Both of them are the same values at the ends. So this is equal to 0, because u of delta of a is equal to 0 and delta of b is equal to 0. So this get doesn't participate anymore. And all I have now is this part plus, instead of this, I will have this. So it's this minus this. Now, in both cases, I have a multiplier delta x, which means what? Which means if delta x is any, then difference between this and this must be equal to 0. df by df of what? X, g of xt and g prime of xt minus this d by dx df of x gxt g prime of xt by df. And if I will substitute t is equal to 0, then I will have to have this is equal to 0. Now, if I will substitute t is equal to 0, g of x 0, so g, remember, is g is f0 of x plus t delta of x, right? So if t is equal to 0, I will have only f0. So I will have df of x, f0 of x, and f prime of x. by df 0. So that's the partial derivative of capital F with argument f equal to f0 minus d by dx df of x f0 of x f prime of x0 by d third argument. And this is supposed to be equal to 0, and this is Euler-Lagrange equation. That's it. Now, if I was maybe a little bit too fast. The notes for this lecture, so you go to unizor.com, go to Physics Plus course, and Variations is the chapter, and in that chapter you have a lecture, Euler-Lagrange equation, and I do suggest you to look all these notes. They are much more detailed than whatever I was just trying to do as fast as possible. So that's where you will get this complete derivation of this. Well, it is also, I mean, I did complete actually, I just was a little bit fast maybe. And I do suggest you actually to make sure that you understand first of all the calculus manipulation, which I did here with partial derivatives and stuff like this. So I'm presuming that calculus is something which you know, obviously, and the previous lectures also are very important within the same functionals and variations type of information. So they are in the previous lectures of the same chapter. So I do suggest you to basically take the course rather than just, if you found, for example, this lecture somewhere by accident on YouTube or somewhere else, well, it's good if you know everything, but it's preferable that you actually take it much more seriously and study it as a course. Okay, that's it for today. Thank you very much, and good luck.